here we have a limit as n approaches infinity of cosine of a over n times square root of n times cosine of 2a over n times square root of n, all the way up to cosine of n times a over n times square root of n. Now, this is obviously an undetermined form, right? Because every cosine, the angle is approaching 0, right? And even this angle is approaching 0, right? N cancel out. So every cosine is approaching 1. How many? N many of them, right? 1 to the infinity. Now I'm going to use, after I take the logarithm on both sides, right? Logarithm. Then I'm going to use Taylor expansion with polynomial piano remainder for cosine, and Taylor expansion for logarithm with piano remainder. Right? So the meaning of little o is that, so for example, we have several sequences, an approaching 0, right? Bn also approaching 0, right? Then let me just compare their speed. Let's just say Bn approach 0 faster than An. Right, so what does that mean? So if Bn can be written as Cn times An, right, where Cn is approaching 0, then we say that Bn is little o of An, right? So meaning, if Bn can be written as a sequence approaching 0 times another sequence also approaching 0, then we say Bn is little o of An, right? Meaning Bn is approaching 0 faster than An, right? This is obvious, right? You have some arbitrarily small amount times some other arbitrarily small, right? So also, even more arbitrarily smaller, just roughly speaking, right? So Bn. For example, 1 over n squared is little o 1 over n, right? Because it's approaching 0 faster than the 1 over n, right? Doesn't have to be unique. 1 over square root of n cubed is little o of 1 over n, right? Obviously. Now, the other fact that if we have little o of, for example, several terms, an plus bn, right? Perhaps just 2 terms, but more terms can be proven in the same way. So, and if Bn approaches 0 faster than An, right? So in other words, if Bn can be written as Cn times An, right? Little o of An, Cn approaching 0. Right, that's what it means. If that's the case, then my claim is that little o of An plus Bn can always be written into little o of the slower guy. That's An. Right, the reason is because little o of An plus Bn in this case can be written as some sequence dn approaching 0, according to the definition, right? Times bracket an plus bn, but bn can be written as cn times an, right? If I just extract an out, right, I'm left with what? 1 plus Cn, where Cn approaches 0. Right? So the whole thing approaches what? This approaches 1. But Dn approaches 0. So still Dn times still approaches 0. Something approaching 0 times An. Right? maybe let's write it as maybe Pn times In, where Pn approaches 0. Right? So Pn stands for Dn times this quantity, right? Still approaching 0. So according to the definition, right, it can be written as some sequence approaching 0 times An, meaning it is little o of An, right? So even if we have more terms, right, can just get rid of all the other faster terms, only left with the slowest guy, right? Little o of the slowest guy. Right? That's always true. I'm going to use this fact for this expansion, for this one. And also, the other fact, if we have little o of some faster guy, Bn, then I can claim that the little o of faster guy can be written as the little o of the slower guy, right? So assuming Bn approaches 0 faster, right? Bn approaching 0 faster. It can be written as Cn times An, Cn approaches 0. I mean, Bn is faster. Now, the reason is simply because little o of Bn can be written as some sequence Dn times Bn. Dn approaching 0, right? Dn times Bn can be written as Cn times In. Cn approaching 0. Dn times Cn also approaching 0. Let's call it Qn. Qn also approaching 0, right? Times In. So, according to the definition, it's really little o of An as n approaches infinity. Right? Little o of some faster guy is always little o of the slower guy. But it's not the other way around, right? Little o of the slower guy cannot be written as little o of the quicker guy. So intuitively it makes perfect sense, right? Since it's approaching 0 faster than the faster guy, right? Then is it approaching 0 faster than the slower guy? Of course. But the other way is wrong. If it's approaching 0 faster than the slower guy, is it approaching 0 faster than the faster guy? Not necessarily. Right? So only works one way. So now we've established the following fact, that if two sequences both approaching 0, An, Bn, if Bn is little o of An, meaning Bn approaches 0 faster than An, then we have the following. Little o of An plus Bn is equal to little o of An. Always true, right? Just get rid of the faster guy, keep the slower guy. Also, little o of the faster guy is equal to little o of the slower guy. Right? Intuitively makes perfect sense. And the intuition for this is that even though Bn is faster than An, right? But doesn't matter because the slower guy will hold this quicker guy back, right? It's holding him back, so it doesn't matter. Still slow, still little o of the slower guy. So that's the intuition. So now I'm gonna call the inside, call it maybe Cn, right? So I'm looking at Cn. Limit of Cn as n approaches infinity is what, right? Maybe I just take the logarithm, right? Log of Cn, obviously, because it's a product, therefore, logarithm will be appropriate. That is equal to log of cosine first thing plus log of cosine second thing, right? So we have sigma sum k from 1 to n log of cosine ka over n times square root of n, right? That's the sign. Now, I'm looking at cosine ka over n times square root of n, right? What is that? For fixed k, right? As n approaches infinity, the inside approaches 0, right? So we can just use Taylor expansion, right? Piano remainder, right? And x approaches 0, right? I'm treating this as my x, right? As x. So that is equal to 1 minus half of x squared, half of n squared times n cubed k squared a squared, right? Plus little o of x cubed k cubed a cubed n cubed times n to the power of 2 over 3. Right? 2 over 3. 3 plus 2 over 3. No, 3 over 2. 3 plus 3 over 2. 9 over 2. N to the power of 9 over 2. Right, that's 4.5. Bigger than 3. So this may be approaching 0 faster than that, yeah, obviously. So now I'm going to use the log Taylor expansion. So therefore log of cosine ka over n times square root of n is equal to log of, right, just copy this down, 1 minus k squared a squared over 2n k cubed plus little o of k cubed a cubed over n to the power of 9 over 2. Right? And that is equal to x plus x. 1 plus x. 1 plus x. I'm treating this as x. Right? It says minus k squared a squared over 2n cubed plus little o of k squared k cubed a cubed n to the power 9 over 2. It says plus little o of this thing, right? Minus k squared a squared over 2n cubed plus little o of says k cubed a cubed n to the power 9 over 2. Right? So we have little o inside little o, but I'm going to deal with that. Now I'm going to deal with the little o within the little o. Right, first, let me just copy down the first term, k squared times a squared over 2 times n cubed. And I'm going to deal with this term also. Right? Little o of k cubed a cubed n 9 over 2 plus. So, like I said, little o of two terms add up together, right? Just simply get rid of the faster term, right? Keep the slower term. Now, which term approaches 0 faster? This term or this term? Right? I believe it's this term, right? So this term is already approaching 0 faster than this term, right? The little o of this term, faster than this term. So also this term is even faster than this term. Why? Because this term, like k cubed a cubed over n to the power 9 over 2, right? divided by the other term, that is negative k squared a squared over 2n cubed. Right? I believe this will approach 0, right? Which tells me this is quicker than that. The reason is because that is equal to k cubed a cubed n to the power of 9 over 2 times, there's a negative sign out here, divided by that, meaning times its reciprocal, that is k squared a squared 2n cubed, right? So that is I still have k times a, twice of k times a, right? This and that, twice of k times a, and this and 4.5 minus 3, n to the power of 3 over 2, right? Constant over n to the power of 3 over 2, obviously approaching 0. Right, so the top is faster than the bottom, right? So this already faster than that. Just get rid of this. Just little o of this slower guy. Right, I don't need the constant, negative 2. I don't need that, right? Just the constant. Don't need that. K squared, a squared. Right. A squared is constant. Don't need that. Right? This is easily verifiable. And this is equal to negative k squared a squared over 2 times n cubed. So I'm going to replace this faster guy with a slower guy, right? Like I said, this is faster than that guy, right? Approaching 0. Little o of the slower guy. Right. I don't need constant. Right? K squared, a squared gone, 2 gone, negative gone, just this. Right? Plus this guy, little o k squared over n cubed. Right? But this I can just factor out the k squared over n cubed. Right? Little o can be treated as some sequence approaching 0. Right? Just factor this out. Still little o of this thing, right? Just get rid of that. But I can replace k with n, make it even slower, right? Make it bigger, meaning make it slower, right? Replace it with a slower term, right? This is also fine. Replace it with n squared, n cubed. Just 1 over n, right? Little o of 1 over n. So I need to do the sum. It says sum from 1 to n, right? So sum from 1 to n is equal to sum this term, right? That is the sum of square term, right? Square number, right? K squared. K goes from 1 to n, right? And we just factor out the a squared, negative a squared, 2n cubed. And there's the formula. Formula is 6 times n plus 1 times 2n plus 1. Right? And plus sum this. Right? That's every term is this. N repeated n times little o of 1 over n. Right? So n can times 1 over n becomes 1. Little o of 1. Right? This is easily verifiable. Little o of 1 approaching 0, obviously. Right? Polynomial. Polynomial is leading term, right? Leading term at the top, right, is what? 2 times n cubed, right? Also, I have 2 times n cubed at the bottom, right? Don't worry about the other terms, right? they just cancel out to be 1. A squared stays, 6 stays, negatives. Right? So that's the only thing that's remaining. Negative a squared over 6. But this is the limit of what? Of log Cn, right? So log Cn approaching this. So I'm looking at Cn, right? Limit of Cn. So limit of Cn must be e to the power of negative a squared over 6.